to make these cool Necker, right? Necker decisions. Well, I've subtracted A and B, and then what am I going to do? This is checking for 0, but there's actually remember the most significant bit? This is represented as bits, right? If the most significant bit is a 1, I know it's a negative number right off the bat. Suppose the most significant bit of the subtraction is a 0. Well, it could either be equal or greater. I need more information to determine which of the two. That information is here. If each output of the subtraction, right, if I subtract this bit from this bit and I get a result of 0, and that bit minus that bit is 0, it means that bit and that bit is the same. This bit and this bit is the same. This bit and this is the same. If this is a 0 and a 0 and a 0 and a 0, then the result is 0. Well, I can use this way. Okay, Mr. Smithson says, okay, inverter, right? This is, let's call this result 0 invert and R1 invert. And then what am I going to do? Put it through an AND gate, right? R2 dot 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 to R what? In MIPS 31 goes through an inverter, and then what? Has to go to, I want to figure out 0 or not. They all have to, this has to be 1 and this 1 and this 1, which meant that this was 0 and this was 0 and this was 0 and this is 0. I have an AND gate is 0 out. Is there a Boolean property that I can invoke here to get rid of 32 NOT gates for my circuit? De Morgan's. What did De Morgan say? De Morgan's law says we're ANDing not this, not this, not this, not this, and we're ANDing it. You can convert that to nor of the uncomplemented. So here's a great case where De Morgan's law is helpful. It got rid of all these inverter gates here. You're going to say, well, can I build this? Yeah, it's the same functionality. But here's the same thing by De Morgan's law without as many gates. What this is saying is that all the output results are 0. If I compare two bits, I subtract them, and I get a 0 and a 0 and a 0 and a 0 and a 0, that means these two are equal. The result is 0 between the two. There's a difference. So let's use that to design BEQ instruction now. We started with this before. We saw the control path, but we didn't see how to generate. Remember, there was a multiplexer sitting there, and I said, well, if they're equal, right, take the branch. If they're not equal, don't take the branch. And I just had a 0 or 1 sitting there. We didn't say how you generate it. Now we're going to generate the control path for that. So what we're going to do here is let's build the BEQ instruction using the 0 flag on the input to the 2 to the 1 mux, which is making a decision. Either take the branch, if they're equal, or don't take the branch. When are they equal? If you subtract the 2 and you get a 0 result, they're equal. That's a cool little thing to keep in mind. So how do we subtract the 2? This is the previous slide. If all the bits are the same, the two values are equal. It means that we have a 0 after we subtracted the 2. There's no difference. Ha ha ha, between, no difference. Literally. So we want that to be causing to take a branch to the word offset, because we're going to take the branch, right? Is a branch equal? So how do we do that? Here's taking the constant, the offset. We convert from word to byte by multiplying by 4. Then we're going to add it to the, is branch relative or absolute? Relative. Branch is relative, so we have to add it to where we're currently at. Where are we currently at? The PC plus 4, okay, is the next instruction. We add that. So let me ask this question. If the 0 flag is 1, which means it's a 0 output, notice that there's an inverter here, right? So if there's a 1, means that the result was 0. This is the 0 and the 1. So we're going to have to do what? We're going to take this branch, right? Which is correct. 1 means take the branch. Every time we have a mux in hardware, it's a decision box in software on your flowchart. It's performing the decision. You're going to say, well, I like to design hardware. Well, hardware is making decisions. We can make it as software either way, but sometimes software is good to prototype than wiring up 32 wires, right? And finding out it doesn't work. We'd make a little prototype in software. Sometimes it helps. So here we're going to wire this up so that when a 1 comes in, we grab all the bits. This is many to 1, right? We grab all the bits that are on this right side. This is the 0 and the 1 data input. Then when the select is 1, we take the branch. How do we do that? Well, we've taken this offset and added it to the PC. Right here, we add it to the PC. Suppose the result is not 0. We don't want to take the branch. It's branch if it's equal. If it's not equal, that means at least 1 bit was different. If at least 1 bit was different, there's a 0 on this line. What's it do? Which is the next instruction to execute? PC plus 4. Because we took this branch. Okay. So what do you guys think? We try another example? I'll let you guys ask a question. So what we've designed here is control for this instruction. You pretty much see everything happening now, right? Where does A and B come in? Remember we have RS and RT, so where's A and B? RS and RT. Do we need to save RD in this to do a branch? No. That's why we don't have one over here. Now it's making more sense, right? If I asked you what's the functional unit inside the, in this case ALU, inside the ALU that we use to implement a BEQ, you would say the subtractor. Since you know the adders implementing a subtractor, you could say adder, right? So we add A plus negative B here, and we compute the 0, is it 0 or not? And that's going to be doing what? Helping us make the decision for branch. Is there anything else we have to do? No, just whatever new PC we need to branch to is what gets loaded. And then we're done with this instruction. So you're telling me this is all the hardware inside for this instruction? Actually, yeah, for implementing this instruction, yes. There's other things that we need to make this instruction execute, like we have to go to memory and get it, and we have tri-state buffers and turning things on and off in the buses, but inside the ALU to implement a BEQ instruction, you only need a subtractor, a mux, and a couple of adders. Now, question, is this adder different than that adder? Yes. You know, this is a separate piece of hardware, right? But they can be designed the same. Right? This can be a carry, ripple carry, this could be carry look ahead, this could be whatever how fast we want to make it run. So this was step 2, calculating the branch address. I already talked through this. And if you don't take the branch else, then we're into this case right here. So let's make it active learning. So I ask you to design branch greater than instruction. It's not hypothetical, actually. It's not inside MIPS. Let me say it again. Inside MIPS, there's no BGT. If you put it in Mars, you'll see that it's actually changed to a SLTI, and then it actually does a branch based on the SLT. There's no BGT hardware. So suppose you wanted to build BGT hardware. Someone wanted to pay you to do it. A couple weeks salary or so. What would you do? How would you do it? Of course, you have to debug this and implement it and lay out and everything, the chip. Okay, but what do you suggest? Well, here's our instruction, RS, RT label. What's the semantics of this instruction? So I'm going to start with that.
RS is greater than RT, and jump to the label.
Exactly. RS, so what I think is you just put whatever this is right between the two operands here. So if the RS greater than is strictly greater than, right? Not GE, right? Greater than equals. GT, greater than, go to label. So suppose we subtract RS minus RT. Oh, no, other way. RT minus RS, because it's greater, right? You can do it either way. Actually, it's true. If you can check, this is back to Necker cubes. And it depends what you see, right? If you're looking for the negative case, if your glass is half empty, you're looking for the positive case. So what I'm going to do is keep my glass half full and say RT minus RS, look for a positive number here. That's telling me that RT is greater than RS. If I see a positive, okay, well, but what, RS greater than RT? Well, this is cool because I got rid of the 0 case by subtracting this way. Now I'm going to look at the sign bit. Remember the most significant over here? The 31st bit. If the 31st bit is set, that means that they're not equal. So I got rid of the BGE case. You can say, let's just see the circuit maybe. So in this case, if I subtract RT minus RS, and suppose I get a negative number. So the first bit is negative flag is set. What's the negative flag? Like I said, it's the most significant bit of your adder. I'm only showing 4 bits. There's actually 32. If that's a 1, it means that what? RS was greater than RT. Were they equal? No, because that would have been a 0, not a 1. So if this negative flag is set, when I subtract RT minus RS, means that this was a negative result, a negative number, which meant that what? RS was greater than RT because I subtracted RT from RS. If I got a negative number, RS must have been greater than RT. Could they be equal? No. They had to be strictly greater. Then what? Negative result causes the branch. Where does that come from? The same circuit we had, taking the constant, right? Converting to byte, and then adding it to the PC plus 4. And if it's a 1, I want to take that branch. What's a 1? The most significant bit of the subtraction. Subtraction zone and adder. Okay. That's taking the branch. And if not, I'm just going to make the other choice. So this line can either be 0 or 1. It's 0 if they're equal, or if RT is greater than RS, or that means RS less than RT. What do you guys think? So I have more examples of this in the study set. We're going to see some more examples here and work at some of it. So next class, we're going to design a multiplier and the multiply instruction out of gates. To use multiply design, we're going to use adders again. Okay, thank you everyone. If you have questions, especially questions about grading, you can see me. I will help you. Okay. Any other issue? Any questions, come see me. Hi everyone. We're going to pick up where we left off with multiplier design today. So let's begin with that, and we have some fun at the end. Remind me, because we can stop around 2:30, and we have vlogger number 2 today. So we'll take a look at that. Okay, let's start with multiplier. So we built an adder. We gave you a few different designs actually for adder. Yeah, you need that today. How about multiplication? So let's look at an example, then we'll see the pattern, and you'll see that multiplying with binary numbers is the same multiplication you already know. So here's an example. If you want to multiply 2 n-bit numbers, you end up with a 2 n-bits result. For example, if we have a number 7 times number 7 is 49. 49 represented as 6 bits is a 32 plus 16 is 48 plus 1 is 49. Okay, so if I start with A times B, we have names for these, multiplier, multiplicand. We'll show you that in the next slide. The product, if this is 3 bits and 3 bits, you have a 6-bit product. So contrast this to adding 2 n-bit numbers. So if I add A plus B, A is 3 bits and B is 3 bits, how much is the result? How many bits? The sum is how many bits? Nope. We did so many examples. All right, I add A and B, and the result is I have 32 bits of A, 32 bits of B, 32 bits of result, plus one bit of carry. So you have, if you have A bits and B bits to get added, you get A and B is equal. If you have A bits and A bits to get added, you have A bits of sum, and you have plus 1 bit of carry. So it's A plus 1, right? A plus 1. What about here? It's A plus B. So it's actually A times 2 if A and B are equal. So in the case of multiplication, another way to think about this, if we're multiplying 2 numbers, in the extreme case, the largest value is 2 to the n minus 1. It's almost equal to 2 to the n. If you multiply something times 2 to the n, it's like shifting it n times to the left. Okay, so if you start with n bits, it's like n shifts. So if you have n, you're going to be getting twice as many at the end. So we're going to see this definition of terms. We have n bits. We won't look at the numbers yet because then it gives a mental block once you see ones and zeros. But n bits and n bits, we're multiplying the two. We have a multiplicand and multiplier. And when we multiply this by pencil and paper method, what do? You multiply this term times this term and you write it here. Then this term times that and write it here. This term times that, write it there, and so forth. But you notice if we started with n bits here, you get a partial product of n bits, then we shift over. Question, why do we shift over on this next row? Why? Because they told you to do it. That's why, right? But why? So now looking back 10 years later, why did you do it? Because this digit is it's weighted one more position to. So this is like saying this is the ones, right? This is the number. This thing multiplied by the number of ones plus this thing multiplied by the number of twos, if these are binary, right? Or tens, right? Distributive property of multiplication over addition. We're taking this number and saying that this can be composed by distributive property. That's what you did when you did pencil and paper method. So how do you get the final product to hand in your fifth grade multiplication? They call it longhand or something, right? Longhand, yeah. So what do you do? You add them up. We build a circuit out of gates, Boolean gates to do this. We're going to do this exactly. We're going to multiply each one of these digits, make these partial products, and use an adder to add them up. Is that easy? Yep. We just do bits instead of decimal digits. So the cool thing, when we make a circuit, hardware, we can actually do these on parallel. Okay, you only have one pencil in your hand, right? I guess if you're like super ambidextrous, you can do like one at the other, I don't know, but we can actually have one circuit computing this, another circuit computing this, another circuit computing this, and we have to add them all up. So we're going to have some trade-offs. The values that we're using here is not 2's complement for right now. You make it 2's complement later. So let's start with the unsigned binary case. You're going to say, well, suppose I want to do sign. There's some ways to do it. There's something called Booth's algorithm. I don't hold you to that because actually it's making it complicated. There's an easy way to handle positive and negative numbers. You can take the XOR of the signs, right? Positive times a positive is what product? Positive, right? Positive times a negative is negative. Positive number times, right? This way. The positive number and positive number, do it this way. Multiply them together. These are your inputs, right? A and B. This is A times B. Positive times a positive is a positive. Positive times a negative is a negative. A negative times a positive is a negative. A negative times a negative is a positive. Does this look like any Boolean function we know? XOR. Okay. You can have cookies or ice cream, but you can't have both. You can have none. So here is our first multiplication with binary digits, but it's multiplication you already know. So don't get a mental block. Okay? So what's the procedure for this? Let's start with putting some numbers to what we just did in the previous slide, what we call the pencil and paper or longhand method. So 13 times 11, so 3 times 1 is 3. 1 times 1 is 1. We shift over, 1 times 3 is 3, 1 times 1 is 1. We add it up, 143. What about binary? Same exact thing. 1 times 1 is 1, 0 times 1 is 0, 1 times 1 is 1. Okay, next one. That turns out to be the same because it's times 1. All right. See, it's getting easier, right? In the binary case, there's actually only 2 cases. See, what do we do here? We considered each multiplier digit separately, and then we multiplied it by the multiplicand. So this is 1 times 13, and another 1 times 13. What about here? This is 1 times this, 1 times this, 0 times this. So what 2 cases do we have here?
You either got the
That's awesome.
number or 0.
Yes. It's Ralph, right?
No, Miguel.
Miguel, okay. Oh, where's Ralph today? He's usually sitting right here. Oh, usually here, right? Oh, okay. He's getting ready for the video. He's got popcorn. So Miguel's pointing out that you get either what? You either get multiplicand they're right there. Get the multiplicand unchanged, or you get 0. Is there any other choice in the world? No. We're going to use that in our circuit. We can use a multiplexer because it's 2 choices. Now it's getting cool. Okay, so how do we get the product? You add it up. 1 plus nothing is, these just come down, right? 1 plus 0 plus 1 is 1. 1. Everybody see the 143? This is 128. You see the 15? What's 128 plus 15? 143. So we conclude, as Miguel did, multiplying binary digits a little bit easier in decimal digits because there's actually only 2 cases instead of a whole bunch of cases, which they made you memorize all those because they, just wanted you to do that. So here, what do we do here? Well, if it's a 0 for the multiplier bit, no worries, write a 0. If the multiplier bit is a 1, we write the multiplicand directly. Is that it? That's it. So here's a flow chart for doing this, okay? And we're going to make a circuit. So first we see the way the circuit works. Somebody having lunch here? Submarines? All right, is there a pizza? I don't know. No. Okay, so what's going on? This one we have multiplicand in the register. And you're going to say, well, wait a minute, why are we 64 bits? Because we have 32 times 32, we might end up with 64. Now this is, in this case, it's giving us extra space. We're going to keep shifting this. So one way to do this, there's 2 ways, right? What we're doing in this case is we keep looking at a different bit of the multiplier. We look at this bit first, and then we look at this bit. We can do the binary, right? We look at this bit first, then this bit, this bit, this bit. So you can think of, we're looking at different bits of the multiplier, or you can say that this bit is sitting here and we're shifting this to left or right. It's actually, you can do either way. So in this is from the book, so we show you this first, and I have about 12 slides that breaks into steps. I think it's clearer, but here's the overview. We start with the multiplicand and multiplier that you want to multiply. This is loaded right justified, and every time we go through this loop, which is 1 bit, we're going to shift it to the left. So we have 64 bits, and we have, starting with 32 bits, is 0. So there's all the zeros here, and then 32 bits from the register. Which register? RS and RT. Where's the RD? Is the product. How many bits in the product? As we mentioned, is the 32 bits times 32 bits. We started with 32, and we had 32 zeros. So 32 bits times 32 bits, 64 bits. Here we're adding a 64-bit ALU only because this thing's 64 bits. Don't let this number worry you yet. But how does this work? We shift the multiplier to the right 1 bit every time we go through this loop. So the first time through, before we shift, what comes out? This is the least significant bit. You can make a note in your notes. They didn't write it here, but this is the least significant bit. For example, we start here. The least significant bit of the multiplier is 1. We want to multiply 1 times each of these digits. But we said if you're multiplying 1 times this, it's just this. So what we're going to do is add the multiplicand if there's a 1. If there's a 0, we add 0. So what we're doing is we're adding each of these partial products, but we keep shifting the multiplicand's weight left by 1. That's going over here. See, every iteration through, we're going to increase the weight, which is a power 2, same as power 10 when you did it in decimal in grade school, by shifting 1 digit to the left. Every iteration through here is 1 digit. A bit's a digit, is a binary digit. So our control test is just a opaque box right now, but inside this is a little logic, okay, we call glue logic, that's going to connect up these circuits is making this decision. If there's a 0, we place a 0. If there's a 1, we place a 1. Is a 0 times multiplicand? Is a 1 times multiplicand? If you multiply something times 0, that means there's nothing to add. If you place a 1, a copy, you're going to add itself. So you're going to add 1 times multiplicand, shifted to that position based on which iteration we're on. So you can see that what I just said in words here. And this is some functional view of the circuit. So again, if we look through this with another example, here's 8 unsigned times 9 unsigned. What's 8 times 9 in decimal? 72. So 8 times 9 is 72. What is this number? What weight is that one? 64 plus is 72. Did it work? Yes, it works. It always works. So here, every time you get an Excel spreadsheet, you wrote 8 and 9, and this is what happened inside, right? It got converted to binary. Who did that? syscall. You typed in 8, and it got converted to bits. It's already in the register as bits. The multiplier hardware did this. What did it do? It took 1 times 8, and then it shifted over here, added 0, added 0, and then it shifts one more time and adds 8, why 8 again? Because this is 1 times 8. Adds it up. 72. So here's an animation. If this is working, I didn't try it. I found this in the summer. Let me see if this is going good today. This one was pretty cool, if it's still out there. Makes it Vegas style slot machine or something, I guess. I don't know. So what you can do is you can put your bits in here and watch them multiply. So here's we can enter 3 in the multiplicand and 7 in the factor. So he calls it multiplicand, and his multiplier he used the word factor. Okay, so we want to multiply 3 times 7. We should get 21. We can see the steps and we can watch the bits flow. It's basically animating multiplication with binary digits as a circuit. We click go, we get actually each add shift step, and you're going to see it's testing each bit of 7, which is the factor, because we're going to either do 1 times 3 or 0 times 3. It gets added. We're going to, that's what I mentioned here. Then we're going to accumulate the sum. His product is actually the register above, and to make it fun, he made carries actually like filling bins of bits, and once the bins get full, then you dump the bin into the next higher power. So let's take a look. So we want to try a 7 and a 3. Maybe. Multiplicand is 7 and factor is 3. So let's see. It looks okay to me, but let me see. You can do either way, right? But let me take a look. If we want to match the slides, it's fine. So 3 in the multiplicand and 7 in factor. You can do either way. So we'll do what we say. 3 in multiplicand and 7 in. Play around with it. Actually, you can see the bits. Yeah? Okay. So I want to go single step here. If you say go, it does the whole thing. And we can go one step at a time. Paste normal, paste step. Okay. So the first time through, we're taking this factor 1, and what we're doing, we're going to take the value 3 and add 3 to the current accumulated value. So what you're seeing here is an accumulator represented as bins. This is the ones. You either have no ones or 1, 1, 2s, 4s. Okay, so now we're going to, what is that? So we had 1 bit at a time, right? This is 1 times 1 is 1. 1 times 1, right? 1 times, this is 1 times actually 2, right? This actually helps you. 1 times 2 is 2. And then what we're going to do, we're going to look at, we can multiply all these zeros, right? But 0 times anything is 0. So I don't think he shows you that. Then what is he going to do next? He's going to go to the next bit, right? Next digit of the, what he calls factor, which is multiplier. So this is 1 times 1 again, 1 times 2 again, and now we're going to have to accumulate to here. So we're going to get a carry, right? Because you add a 1 to this, you're going to get 2, but we can't represent 2 here, either represent 0 or 1. So once you go here, it carries, you're going to watch. It's kind of cool. Yeah. Oh, that's right, we're moved over, we shifted. So now we've actually added 2 to this. Now we're going to get carry. He does a carry. All right, cool. Then what? We're going to multiply 1 times I'm sorry, 2 times 2 is 4. So we're going to end up with a 4. We get a carry again. And to handle the carry, we're going to move to here. Okay. Then we still have one more digit in the factor, which is a multiplier. So that was 1 times 4 is 1 4. And 1 8. 4 times 2 is 8. We already carried, so that's 16. I think we're almost done. Oh, 0. 0 times anything is 0. Woo! All right, so what is the number that came out? 116 plus a 4 plus a 1 is 21. So here's a nice animation. This guy was from Spain. Looked pretty cool. It's the best one I could find. And if you want to see some coolness, put some big numbers in here and just turn it on go. Normal. If you get bored. This is what's happening inside the circuit, actually, but these are, because we're electrical engineers, these are not marbles. What are they?
Bits.
They're bits, which are, because we're electrical engineers, we know they are voltages, switching between 0 and 1.2 volts, or 1 volt, or 0.8 volts. We're switching these values on and off. Okay. As voltages. Okay. So let's see. So what we're going to do here, this is just going ahead so you can see where we're headed, right? What we're going to do is we're going to multiply using this method. It's called add and shift. I'm going to show you 2 multipliers. This is the add and right shift method, which is one version of what we just saw in the flow chart and the same thing we just saw in the slot machine. But what I've done is I've simplified this, I think, a little bit, and I got these from a professor I know at Brigham Young that are already pretty organized, and I just reorganized a little bit for you guys. So here, we want to start off with some initial conditions, multiply 5 times 3, and the result is 15. So here's the multiplicand register, and here's the product register, and again, we're just going to do 4 bits because 32 is too many to do by hand. But I have a bit register here is 2 n bits wide, and the n is 4. Right? So here's 5, and this is the product is going to be 2 n bits, because when we multiply n bits times n bits, I get 2 n bits. And the way this works in the add and right shift is I'm going to add. I'm going to put that in the shift register, and then shift it right. Okay. So we're going to keep doing this here. We keep shifting this right. So first we want to multiply 5 times 3. 5 is the multiplicand, 3 is the multiplier. And other things in the circuit. We have a multiplexer making a decision. What is this doing? Can anybody describe in words? Is Neil.
It's going to choose between 0 and 1. If it's 0, then it's going to
Awesome.
go down.
Exactly. So this is choosing either to add 0 to the value or add 1 to the value based on what?
Based on the bit.
The least significant bit of the multiplier, which is the same decision we did with pencil and paper method, except now we're using registers and hardware. Okay. So let's take a look. So first we do add, then we do load, then we do shift, and we keep repeating that until this register is emptied. Okay, so what happens? Least significant bit is 1. So which do we select? This input of the mux, that's going to add the multiplicand to the previous value of the adder. What value is coming in the adder? The upper 4 bits of the product. Okay, so we take this, which was 0, because we initialized it. We add 0 to 5, you get 5. Then what we're going to do is load that into this product register. So we did the add, now we do the load. Then we're going to do a shift operation. Shift operation we shift the product to the right. You're going to say, well, wait a minute, doesn't the product get more weight every time? Actually, yes, but what we're going to do is it's just like you can move to the left or you can move the window to the right and it's the same effect, right? So here we're actually writing the bits here and we keep shifting this to the right. So the last time through it has the most weight. The first time through it had the least weight because by the time it gets to the end, that meant it had the least weight because we keep shifting it to the right. So now we shift this to the right 1 bit. What's shift do? Always introduce 0. Then what? Next bit. So now a 1 is the least significant bit. We're going to add the multiplicand again, but what does it add to? 0, 1, 0. So what's 5 plus 2? 7. Next step, load. We're going to load the 7, right? So you're going to say, well, when do things happen? So the first step is add. This is what comes out of the adder. When the next clock comes, this is 1 clock cycle each, which we're going to do some calculations of clocks per instruction for a multiply, the CPI. When the first clock comes, we add. The addition's ready then after 1 clock. These inputs are sitting here waiting to come into the register. What's inside this is the circuit. What component did we learn in 3342 that's inside this? D flip-flops, right? So when the clock comes for load, the value that's applied gets loaded in. To where? The upper 4 bits. So we see that here. Does it overwrite what's there? Yes. That's what D flip-flops do. When the clock comes, it loads whatever value is applied on the input. When the next clock comes, since it's a shift register, we're going to shift. There's also shift register, and we're ready for the next bit. So now you have a 0 in this digit. You're going to add 0 to what? This upper 4 bit. Adder. 0 plus 3 is 3. Next clock cycle comes, it's time to load. 3 gets loaded. Time to shift. Now we got this digit of 0, the same thing as like the last time. We're going to add 0 to this value, it's just itself. Time to load. We did the add, now time to load. Time to shift. Okay. It's the last step. Final conditions. How do we know it's the last step? Well, there's 4 bits here. We have to do 4 iterations. We have to multiply. All right, we have to multiply each bit of the multiplier times the multiplicand. The same thing you did pencil and paper. All right. So when the multiplier is empty, it's done. You can think of it that way. There's 4 bits. We had to shift 4 times. What did you end up with? 15. What did we start with? 5 and 3. Okay. Question, you said, well, we lost the multiplier. Is true. This is destructive shift, but that's okay because this can be reloaded on the next multiply instruction anyway. What we cared about mainly was the product. Okay. So let's do some analysis of how this circuit works and how fast it works, and then we'll make it better. So, time versus space trade-offs for multiplication. Just like we did for adder, right? We had different adders, we had different multipliers. Actually, there's many, many designs. So let's look at just a couple. We can use 1 adder and 2 shift registers. Oh, these are actually the shift registers. This is just a regular register, right? So 1 adder, 2 shift registers, 1 regular register, and a mux. So the space cost is not huge. You know, for doing multiplication, that's not too much hardware, really. Actually, we're going to show you a lot more hardware in a second. What's the problem is a high time cost. Let's calculate it. Well, we had W bits. Let's say, suppose we had a W bit word. What's W for MIPS? 32. 32 bits per register, right? You multiply 32 bits times 30 bits. So how many iterations of that do you have to do in MIPS? If you were using that multiplier? 32. So W is 32. How long does each iteration take? Well, there's some time to add. There's some time to load the register. There's some time to shift the register. So it's W times T add plus T load plus T shift. If each one of these is a nanosecond, like your clock period is 1 nanosecond, so your time of add's 1 nano, Time of load's 1 nano. Time of shift's 1 nano. How long does multiply take using this multiplier on that processor? 96 nanoseconds. That's pretty long compared to when we're used to executing quick. So if the clock is 1 nanosecond, it takes 96. What's the CPI for multiply using this design? Remember we had CPI of add and CPI of everything. What's CPI multiply using this add and right shift multiplier? You got it, right? Using this design, add and right shift is 96. That's 0.0. Is that a large number for CPI or a small number? That's pretty large. So we can have a faster design? Yes. Okay, we do multiplies a lot. Every time we watch a video, they're doing threshold, they're actually converting the data coming in to something that they can display. There's a lot of, every time we do signal processing, you like, these topics are very cool actually. You can take EEL 4750, which is DSP, digital signal processing. What does that mean, digital signal processing? It means just what it says. In the old days, which is not that old, like the 1980s, okay, microprocessors weren't that good because we only had 10,000 transistors or 60,000 transistors. So we did analog signal processing. What does that mean? We did filters, okay? And what do we do when we do filters? Time constants, right? And you put a capacitor and inductor and you make a tank, right? And the signal comes in and you try to filter out this. You make a notch filter, you make a bandpass filter, right? If you haven't seen it, you'll see it soon. That's analog signal processing. What's the problem with that? It's not very programmable. The great thing about digital signal processing is we say, you know what, that's too hard. That's great for physics and drawing squiggles on the board, but the real way we do everything these days is what do we do? Convert to binary right off the bat. Somebody keep asking me this question. Actually, it's a good question. He's an audiophile. He's a guitar player. You know, how's this? What's my MIDI box do, and how does it work? Well, actually, the first thing right off the bat, they just convert to bits, and the rest of the time they do digital signal processing. That says that it's easier just to crunch the bits. Multiply and multiply accumulate are the most fundamental steps. So it turns out multiply we do a lot in DSP. We do a lot of signal processing on our PCs today or phones, okay? When you talk to somebody, it's all DSP, okay? They're filtering out noise, they're correcting error codes, that's all DSP. Multiply is very important, so how can we make multiply faster? Here's a hint. Remember we said here, sorry for so many back, we said here, somewhere, we can form all these in parallel, right, if you had enough arms, right? Well, we can make as many of these circuits calculating each partial product in parallel, then we can just add them up. Something very cool is going to happen here. We're going to see this can be done very quickly, but we're going to see something else that to me got me really interested when I was first saw this topic, that there's some limit to this. No matter how many, it's like Amdahl's law, but it's even like a stronger property, that you can't make it faster than a certain amount. No matter how hard you try, actually. It's very interesting. So the basic approach, this is the first design, was we call add, load shift is add and right shift multiplier. The second approach is we're going to call as array multiplier. We're going to generate all the partial products in a single step. Then we're going to all add them up. And we're going to use these adders shaped in a tree. And that's the interesting part. So here's a thought question. Before we design the circuit, what's the minimum time to add n numbers? So for example, let's just take these numbers here. Help me out. 4, 3, 1.
5. 2, 4, 3.
2, 4, 3?
2.
Did I get it right? Actually, it doesn't matter. It's this hypothetical one, but that's fine. So, question. If I've just doing this problem by myself, how would I add up this? I want to compute the sum of, I want to compute the sum of x sub I, okay? And here is x is a vector, okay? I want to compute the sum of each element of this vector. I want to compute the sum of this. So how do I do it? So I can just add these two, right, and get 7, and then do what? 7 plus 1 is 8, and I get 8 plus 5, 13. Okay. Suppose this would be like having one core. Suppose I have 2 cores. How can I add this faster? You can add pairs. Okay. Mr. Price is on the right track. So,
And use the second core to add the next bit.
so what I'm going to do, I have time running this way, and actually this is space in this dimension. Now I only have 2 cores, but suppose I had 4 cores. If I had 4 cores on core number 1, I can add 4 and 3 and get 7. What is core 2 doing while core number 1 is adding this pair? It's adding the second pair. It gets 6. If add takes, whatever, 1 nanosecond, this took 1 nanosecond to get this, but then at that 1 nanosecond we had 2 results, but we have another core, we got another result. And core 4 got result 5. Then what do we do the next time? This is time equals time step 1, and then what at time step 2 what? I only need 2 cores, but I can have any of the cores I want, but core 1 and core 2 can be busy doing what? 7 plus 6 and get 13. At the same time, core 2 gets 11. And what happens at time 3? Well, maybe core number 1, I don't know, we'll add these and get 24. So if I had 1 core, how long did it take to add up n numbers? This is computing I, sum of I, 1 to n. This took how many steps on, it's a question, on one processor? It takes n minus 1, okay, because here's, you have to do 1 add, and then you have to add that to that, because the first add is adding 2, right? Then after that, each one. So it's actually n minus 1 steps. We say, if you haven't seen this before, it's just saying what is the trend without the constant. We say it's order n, which means it's proportional to n. This is just a mathematical way of saying proportional. This time is proportional to n on one processor. I'll just say 1 processing unit, okay? Processing unit. Suppose we had 4 processing units. What's the execution time? So only 3 time units. Question. Can I add up? Question. Can I add up n numbers? Let's give you first constants, right? Give you some. Can I add up 8 numbers in less than 3 time units? No, you can't. I'm giving you the assumption here is a dyadic adder, which is actually how we build it. You can build a triadic, but nobody does it. Actually, the truth table is getting it, but it's not really worth it. But anyway, if we have dyadic adders, it takes at least 3 time units. What's the relationship between 3 and 8? Say again? 2 to the n, exactly. See, powers of 2. Powers of 2 are all over. It's like calculus the first day, learning derivative, right? It's a good one to know. They're going to keep coming back. So what do we have here? We had 2, see, 3 levels, right? So we had this, we double it, we double it, we double it. So each time we doubled it. Going the other way is log n, see? 8 is log base 2. 3 is log base 2 of 8. What is it saying is actually, this time is the ceiling of this. In case this is not a power 2, then you're going to go to the next time unit because you have some wasted stuff here just to get the next level. But what's the point? The way to think of this, which is a very good insight when we design hardware, we started out with a problem of adding n numbers. The least we can do, The least amount we can have later, or they can say the most work we can get done in one time step, is to take a problem of n numbers and to add and convert it to adding n over 2 numbers. So here we had n numbers to add. And then at this, how many numbers did we have to add? N over 2. And then here we had how many numbers to add? N over 4. And here we end up with n over 8, which is one number. So what we did is we started with a problem of size n. In one time step, we reduced a problem of size n to a problem of size n over 2. So now let n equal n over 2. Apply again, you get n over 4, right? So we're cutting the problem size in half every time. We say that this runs in order log time. Log base 2. Okay. That's the fastest you can add up n numbers. There's no way to make that faster. Okay? Why? Because each time we cut the problem size in half, actually when we cut the problem size in half, we're doing really good. Okay? If I give you a problem, you know, something to do, and in one time unit you have half the work that I had the time unit before, and then you do the same thing again, you have half that. You can get big problems done really quick. That's what we want to do here. We have a lot of bits to add. We're going to put the adders in a tree. Okay. When you do it in pencil and paper, how did you do your add? I don't know. Maybe you were like Gauss. I don't know, in 5th grade, right? What's the story with Gauss, 5th grade? How did you add you did your adds one at a time, right? Most people do, right? You just add this up, right? We generate this partial product and we added them up. But you can add these in a tree, which is where we're going to build it, right? What's the story on Gauss? It's aside, but it's fun, right? The teacher, it was supposed, I don't know, they say it's supposedly true, but then they don't have like actual records. Okay. Gauss is talking in class in 5th grade, and the teacher wants, you know, them to study, and they think they were doing some multiplication and stuff. So anyway, the teacher asked to compute the sum of I from I equals 1. I think this is the way the story goes to 1,000, right? Is it boring? Gauss came back right away with the answer. She thought, well, this is going to keep them busy, you know, start them up, right? Give them something to do and they'll stop talking and work, right? So how did he come back with what the sum of the first 1,000 numbers is right away? Yes, and why? Why does it work?
N minus 1 over 2. N top n minus 1 over 2.
So it's n occurrences of the average value. What's the average value of this list? Well, the first number is 1. What's the largest value here? N? And how many, so this is n occurrences of the average, right? The average is 1, this is the lowest plus the highest, and divide. N squared. Right, so he has n occurrences of the average value, right? No, what am I doing wrong? So he said the average value is 1,001. Divide 2 is the average. Duh. Okay. This is the average, right? Okay, because the highest and lowest is, yeah. So n over 2. If we Google this one, he calculated this as a series, looking for the trend in the series. Gauss. Young Gauss. Oh. So looking for the trend here, the largest number was even, you can add the pair, so on and so forth. And so he said that there was n elements. See, n elements of the average value. The average value is 1 plus n. And factor into this. So what's the point? So the point is that if we know some property of the sequence, we can even do it faster. But in general, if you want to add n numbers, the fastest time you can do n arbitrary numbers, okay? Not a sequence, okay? N arbitrary values. The fastest time is log, see, it's actually ceiling, log base 2 of n. If n's a power of 2, you don't need the ceiling. If n is not a power of 2, then the ceiling will go to the next highest value. You'll have some empty leaves in the tree. So let's take a look. Let's build a circuit. Turns out it's actually one of the fastest multipliers you can design. This is what it looks like, putting this concept into a circuit. So let's take a look at how this circuit works. It has two components. We call it AND array and a tree. So the AND array is actually generating all these partial products. Now, this is the cool part, is we can do this in one clock cycle. How is that? You notice here, if I have A times B, this is A0 times B0 is what gets written here. I'm writing this as bits. It means multiply. A1 times B0 is written here, right? Because we multiply this times this and write it here. We multiply this times this and write it here. Then we shift over. You multiply this times this and write it here. We're always multiplying by B here, right? B1, 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 B2, 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 B2. So what's interesting, if I go to multiply 2 bits, there's only 2 choices. One times 0 is 0. 1 times 1 is 1. Also 0 times 0 is 0, right? So anytime I have a 0, I get a 0 result. Anytime I have the only time I have 1 result is 1. What does the truth table look like that? If this is A and B, it is an AND gate. So A can be 0, B can be 0. These are bits, right? These are bits. You say, why did I write this? Well, these are bits. That's another thing too, right? After so many times you write this, all of a sudden you realize what it means, right? This is all the combinations, right? This is a binary number. So if there's 2 binary numbers, that can be 0, that can be 0. If this is 0, then that can also be 1 because they're independent bits. Then you're done, right? For this case is 0. If this is a 1, that could have been a 0. If this is a 1, it could have been a 1. That's the cases. So we're saying here, if 0 times 0 is 0, 0 times 1 is 0, 1 times 0 is 0, this is A times B, which we're writing over here as just AB with no, just shorthand. 1 times 1 is 1. Is that any Boolean function we know? It is AND. This is so cool. To multiply 2 bits, what gate is it? An AND gate. This is, an AND gate generates A times B. Really? Yeah. You multiply a single bit times a single bit, all you need to do that as an AND gate. Question. If I want to compute all these partial products in one time step, how many gates do I need and what type? I want to generate, let me say the question again. I want to generate all my partial products in a single time step. How many gates do I need and what type? Make it a specific problem. So this problem here, a 4-bit number times a 4-bit number. I want to multiply 4 bits times 4 bits. I want to generate all the partial products. How many gates do I need? In one cycle. Well, I can put an AND gate for this, an AND gate for this, AND gate for this. You need 16. You can do anything in between, actually. You can do one clock cycle, you can have 4 AND gates and do the first partial product at the first time. And then the next clock cycle, you can compute the next row, and then the next row, or you can do this, right? You can take A0 and B0, let's replace each one of these, it's actually AND, let's replace it with